Good morning everyone. I am Jayachandran J, Assistant Professor, Department of Mechanical Engineering, Emmanuel JJ College of Engineering, Natalam. Before we begin, let me give you a brief introduction to the topic non-traditional machining processes. In conventional or traditional machining, we use tools like lathes, milling machines, or drills where material is removed mainly by mechanical cutting using a harder tool. However, as materials have become tougher and more complex, such as hard alloys, composites, and ceramics, traditional methods often fail to provide the required precision, surface finish, or efficiency. That's where non-traditional machining processes come in. These are advanced techniques that remove material using electrical, chemical, thermal, or even mechanical energy rather than just mechanical cutting. Examples include EDM, that is electrical discharge machining, ECM, electrochemical machining, laser beam machining, etc. Coming to the outline, first one is abrasive grinding, and the second one is non-traditional machining processes. In non-traditional machining processes, different processes include ultrasonic machining, abrasive water jet machining, chemical machining, electrochemical machining, electrochemical grinding, electro discharge machining, laser beam machining, and in the final topic, case studies and overall process comparisons. Coming to the topic grinding, grinding is one of the most widely used finishing processes in manufacturing. Unlike conventional cutting, grinding uses abrasive particles, tiny hard materials bonded together, to remove very small amounts of material from a workpiece surface. These abrasive grains act like small cutting edges, producing a fine surface finish and high dimensional accuracy. Abrasive grinding is commonly used when precision surface quality and tight tolerances are required, such as the production of tools, engine components, and hardened steels. It can also be used for both shaping and finishing materials that are too hard for traditional machining processes and methods. In abrasive grinding, in this picture, can be viewed as multiple very small cutting edges that results in a very fine finish, can leave residual stresses, slow small material removal rates, and sparking out. The standard grinding wheel designations are designed. While this is specific to grinding, realize that there are similar standard designations in most industries. Take the time to learn the standard designations early so that you can speak intelligibly with those within the industry. Coming to the process, ultrasonic machining. Ultrasonic machining is one kind of grinding method. It is also known as ultrasonic grinding or impact grinding. The term ultrasonic refers to waves of high frequency. Human ear can hear the sound waves between 20 Hz to 20 kHz. This range is known as audible range. The sound waves which have frequencies less than the audible range are called infrasonic waves. The sound waves having frequencies above the audible range are known as ultrasonic waves. The ultrasonic machining process is suitable only for hard and brittle materials like carbides, glass, ceramics, silicon, precious stones, germanium, titanium, tungsten, tool steels, die steels, etc. Coming to the principle of ultrasonic machining process. In this machining method, a slurry of small abrasive particles are forced against the workpiece by means of a vibrating tool and it causes the removal of metal from the workpiece in the form of extremely small chips. The workpiece is gradually eroded away. That's why the picture shows the different components and setup of this ultrasonic machining process. Coming to the next process called water jet machining and abrasive water jet machining. The abrasive water jet and water jet examples are shown in this figure. Coming to abrasive water jet machining, it is an extension of abrasive jet machining process. In this process, high pressure and high velocity stream of water is used to cut the relatively soft and non-metallic materials like paper boards, wood, plastics, rubber, fiberglass, leather, etc. The principle of operation for the water jet machining is when the high velocity of water jet comes out of the nozzle and strikes the material, its kinetic energy is converted into pressure energy, including high stress in the work material. When this induced stress exceeds the ultimate stress of the material, small chips of the material get loosened and fresh surface is exposed. The schematic arrangement shows the inlet water is flow through the accumulator by using jewel or control valve. The abrasive particles mix up with the water and coming out through the nozzle to the workpiece. So high or tight tolerances achievable to this machining process. Jet will lag machine position, so controls must plan for it. Coming to the next process, chemical machining, or also called chemilling. This is the process. The material is removed from the workpiece through a controlled etching or chemical attack of the workpiece material, so that the material can be removed from selected area of a workpiece or from the entire surface of the workpiece according to the requirement. If selective machining is decided, the areas of the workpiece which are not to be machined are covered with a resistant material called a resist or maskant. The workpiece to be machined is first cleaned in trichloroethylene vapor or in a solution of mild alkaline at 85 to 90 degrees Celsius, followed by washing in a clean water. This removes dust and oil from the workpiece. After cleaning, the workpiece is dried and coated with the maskant material. In order to obtain a uniform depth of metal removal, temperature control and